And be truthful and honest. This is a concept that at times gets taught in Calc 2, right? So you're really again saying, why are we doing it now, Mr. Roy? Well, because we can. And some of us are moving on to take Calc 2, and we'll take Calc 2 in the future time. And hopefully this will give you just a little preview into it. But secondly, though, this isn't anything that's overly, I don't think, overly tough. That's something you can handle. Just another way to integrate special circumstances and cases. We're going to use some words here. The word converge, the word diverge. Some of you maybe have listened when I was showing the people that were gone of this kind of same idea of what it means, so you already have an idea of what it is. But let's start. And this goes back to that number or whatever we just looked at, 20 whatever, 22 or 24. Here's a fast question to ask you. Could you take the integral of 1 over x from 3 to 6? So let's just look at, see if we can take an integral, definite integral, find the exact area. So those of you that are wanting to use natural log, is this a natural log worthy problem? No. Why not, Ashley? Because it's an x squared, right? It's not x to the first on the bottom. My function's not to the first power. Just refresh and remind. What should we get to? If you get the answer then too, I would argue, could you graph that function and just take a peek at what the graph's going to look like? We're actually going to use this function to investigate some other things.
So we graph the integral?
So what's the graph of 1 over x squared look like?
Oh, okay.
You know, and what does that mean? 3 to 6. I mean, from 3 to 6, it's the 1, a definite integral. We're going to work a lot with definite integrals here. We're going to have to evaluate kind of by hand here what they are. None of them are going to be overly able to look at what it is. What we're shooting for, looking over here, I'm like, hey, that's right. No, sorry, I saw this, but that's not, it wasn't the sign. So you want 1 over 6 for an area? Because what's another way to write this? Another way to write this would be x to the negative second, maybe, if I wrote it that way. And that's, again, not a natural log worthy because it's not x to the first. What's the integral of x to the negative second? Do what to my 2? And then I have to, divide by negative 1 or have this negative 1. Now I'm evaluating at 6 and 3. I would maybe argue another way to think of this, though. This is like having negative 1 over x. Which one do I evaluate first? 6. So this is negative 1 over 6 minus. So minus the negative, what happens? Plus. So what's negative 1/6 plus 1/3?
Regular 1/6.
Regular 1/6. How's that a regular 1/6? How do I add fractions? Common denominator. So my common denominator would be 6. I have a negative 1/6. My other one would be, if I change this to 6, would be 2/6. So what's negative 1 plus 2? Positive 1. You get a positive 1 over 6. What's this look like as a function? If you graph this, I'm going to take a moment to real fast. What's this look like as a function? 1 over x squared. Christy did the band directing, and this is maybe what you get. I always question how they do that. So like this-ish. What does this mean again? Just to get an understanding, because that's going to be kind of key today. What's 3 to 6 mean? Bound. So what are you, this answer of 1/6 is saying that from 3 to 6, this is what? Would that make sense maybe, right? Is there a lot of area between 3 and 6 on this function? When you look at your calculator? Yeah, no. Now, we've done this, it's been a while ago, right, where we spent a lot of time with definite integrals, right? Today, improper integration, though, here's where we're going to take this to another level, though, is there's always people that ask the question, what if? What if my bounds don't go from 3 to 6? What if I asked you to find the area from, say, 3 to infinity? What if, right? My two oldest sons are in, like, I don't know, infinity. I've told you some stories like every night it's like, hey Dad, what's infinity plus 1? And I'm like, yeah, it's infinity. And like they know these things, it's kind of funny now and stuff, but they have no idea what infinity really is yet. But they talk about it all the time. Well, what would happen about my area here? Because you already have kind of the idea, right? What's the graph of this going to look like? The graph is going to look like, I don't know if you can see my graph. Look like this-ish, right?
Yeah.
Do you get, like, is this function ever going to go to 0? You know, is it ever going to get to the 0, even go below 0? It just gets closer and closer and closer to 0. But will it ever get to 0? So am I always going to have a little sliver of area under there? Again, infinity's quite a ways out that way. So here's my answer to ask you. What's the answer going to be? Do I get an answer like, hey, the area is 5?
No.
Or do I get an answer of like, the area is infinite?
No.
Because my function goes on forever. And that's the question, and this is why they call these improper integrals, improper integrations, because I'm going to infinity, and so my bound is something that doesn't even truly exist, right? But we can do this. Any guesses how we do this? How do you go to infinity?
Limits.
Use some limits with this. And so what we're going to look at today is you're going to do this same thing, this integral from 3 to, instead of calling it infinity here, I'm going to call this actually, I think in a moment here I use the letter b here is what I use. But I'm going to say from 3 to b of, 1 over x squared dx, which we already did this, so that should be easy. But I technically, since I can't go to infinity, the calculus says if I can get really, really close to it, how do I get really, really close to something is I can take the limit as b goes to infinity. And we can answer this question, is it going to be an infinite amount of area, or is it going to be some finite number? And so when you do this though, here's what really the thing is, you're still going to integrate. So it's going to look like this, almost ignore the limit piece. Then at the very end, after we integrate and plug in 3 and this b, we're going to look at what happens as b goes to infinity and just take the limit. That's the only difference. So integration and limits kind of all in one. So tell me again, what's the antiderivative of this? We just did it.
Negative 1 over x.
It's negative 1 over x, right? And I have to evaluate this at b and 3. And in a moment here after we do that, we're going to take the limit as b goes to infinity and find out what our answer is. So which one do I plug in first? B. So this would say negative 1 over b plus or minus, and then again I have negative 1 over, plug in 3, minus the negative is going to make it positive, and it's still at the end now. Now here's where we get to the point where I have to take a limit. What happens when I plug in infinity in for what? I'm plugging in for b. So what happens? Negative 1 over something huge. Really small. How small?
Infinitely 0.
Thank you. So this would be really, really close to, is that true? That'd be really, really close to 0? What happens when I take the limit of 1/3 as b goes to infinity of 1/3? this would say, what's my answer?
1/3.
This would say that I actually have an area under my curve of 1/3. That's not more than 1/6 that we had before we went from 3 to 6. Yeah, and again, it should be, right? Because I'm going how far to past 6? I'm going infinitely past 6 there. But what it actually is saying, though, even though I'm going to infinity, there's always a little bit of area there. That amount of area there is so small and it's changing, it's so close to 0 that even when I add up those infinite number of pieces, it's going to turn out to be a finite area, which is weird to think. Is this always going to happen and always be the case? Maybe not. Now we say, here's the word for this. If my answer, when I do this, if I get a finite number, right? This is a number, this is not infinite, so this is a finite value, finite number. We say that my integral converges. So if I get a number out for an answer, we say that our answer converges. And so they're going to ask you today on the assignments, does this integral diverge or converge? Converge means that I get a finite number. Diverge is going to mean, what do you think you get for an answer? You get an infinite number, an infinite value. That's what we're going to look at today. What happens as things go to infinity, or what kind of areas do I get under my curve? Is this going to be much different than what we've done before? The only difference is at the end you have to take a what? Good, bad? Should we look at more? I don't know if you want notes here. This is the definition of an improper integration integral. I don't know if you need to write it down, but the way they define it is it's a definite integral, right? Definite integral, I have bounds. It's just that either one or both of my bounds involve infinity. Or the other possible case that happens is that as I take it, potentially my function won't exist. And so the integrand that approaches infinity at one or both ends, or the first part here, sorry, that either one or both limits are infinite in that integral. I'll show you an example of what that means. So that means just as, if I ask this for the same question, which we're going to do in a second here, what if I went from 2 to 2 and said, what's this area? Thank you. What happens from -2 to 2? This has what if I go, how far high does this go? Infinitely. And same way on this side, this goes to infinity here. Is this going to have a finite amount of area or an infinite amount of area between those two? Infinite. And that's what we're going to investigate and look at. But again, this does have set bounds. It's not like I'm going to infinity. It's just that my function goes to infinity between those set bounds.
Will we ever come across one that's like from -2 to infinity on a graph like that? Since you have 2 infinities in it.
You probably won't, but you could. But you probably won't. But it would be doable. I'll show you how we could do it. I don't think you'll see any of those. And again, another way why they call them improper integrals is really definite integrals come from the fundamental theorem of calculus, which came from adding up an infinite number of Riemann sums. It's just that how many Riemann sums am I going to add up here? An infinite amount, which is that possible to do? In some ways, calculus, you wonder, is it possible to do? But limits it is, but that's why they call it improper integration, because it's not like a normal integral, it's improper. You guys aren't very excited about this either, are you?
Who's got treats this week?
The other thing I'm going to just right now, and we'll look at some more here. Other thing to look at is what if, maybe Ashley, write these down. This is the general formulas. I don't know if you need to know this. You do need to know this. When I say why do you need it, I don't think you need to. These would be if one of my bounds is some number and I go to infinity, like we just talked about a second ago. Really where my infinity is, I chose b here. And so I'm taking the limit as b goes to infinity of that. I could actually look the opposite, going from negative infinity to some set point. So this is kind of what they call type 1.
Why do you use the letter B?
goes back to the fundamental theorem of calculus. It just in terms of when you write out the definition of a definite integral, they always write it from A to B. And so, Will, that's just notation they use. Do we have to use it? No, it's just a value. But it's just saying, you know, what's the area under my curve from A to B? They use that notation. And so I just kept using it. The bottom one's going to be the one that's a little bit different, and that's the case where the type 2, where my function, and we'll do one of these, where my function is going to go to infinity. So if I said again from this is A and this is B over here, my area I'm going to go to infinity.
Wait, does that say limit going to infinity? It looks like it says limit going to C. On the bottom of.
It does, and so I'm throwing in a the y c. C is actually the place where my function would be discontinuous at. And so, like in this problem here, and this is the one we'll look at the same one before, is that x 1 over x squared one. At C is where my function goes to infinity at. And so C is going to be the value I want to know as A goes to C, what happens, and then as C to B, what happens. But it's discontinuous. I have this vertical asymptote in some ways at x equals C. In all, you'll see. But I end up getting two pieces here. I have to evaluate the left side, so from A to C. That's kind of right here, this side. Then also evaluate the other side from B to C, or C to B. But it's at that value where it goes to infinity. So there's two types of these that we'd look at. Treats, by the way, anybody know if they're up? This is what, the 17th? Chad? Chad? Chad's up? Tomorrow is Friday, though, isn't it? Gosh. He goes fast.
Do you have any line paper?
Maybe.
Doesn't it have holes
Maybe. So jot these down. We're going to use these, though. Then let's... bunch, probably more than you need.
Is it that like old?
Yeah, it's a little vintage. Right now, I have these new paper here. The idea makes sense, though, again, because can I physically go to infinity and find the area under the curve? No. And so how we get around that again is we take the limits as I get close to infinity, or as I get close to negative infinity if I'm going the other direction. So even the second case is talking about if I had something of this nature, as this goes to negative infinity, what's the area under my curve from negative infinity to some value? I can do kind of the same idea as before. So now the two other words I think we already noted this. Converge means that it's actually, if we say that my integral converges if it goes to, and I get a finite value. The word converge means I actually do it for an answer. There's a finite amount of area there. Diverge means that I have a infinite amount of area under there, and it's not going to ever.
Why is it infinite, not infinite? And it's finite.
Why is it infinite and not, say it again, not what?
Infinite,
Infinite.
since it's finite.
Someone who ever created the English word, English vocabulary, I don't know why. I can't answer your question, but there's so many rules that are different in English, right? English is the most complicated language of any of them. I don't know.
It's the second most complicated language.
What's the first?
I don't know.
least my wife tells me that and stuff, and she's a Spanish and English major, but English has all these
Yeah,
different
but
rules.
Spanish has the gender stuff, which we know.
True. But in English, I'm trying to teach my son how to read rights and different things, reading, there's so many different rules, like an EE and an EA, and like they have different,
Right before E, except after C.
well, they have different pronunciations, depending on special rules, that we have. But let's do, I don't know, do you want an easy one or a hard one? Let's look at this. Let's do easy here. Let's do easy. You can do this one. We're gonna go in reverse order here. Tell me what happens here. So here's an easy one. So we just did something like this. What happens? I go from 3 to infinity of x squared. Now, before you even do this, make some guesses here. What do you think? Do you have an infinite amount of area? Is it going to diverge, or do you think you're going to have a finite amount of area here? So what would the graph of this look like? This could be a parabola, and I want to look at what side of the parabola. Right side. So if I think I made this on here. So I'm looking at, say, from 3 all the way to. What do you think the answer is going to be, right? I think more likely it's going to probably diverge, right? Does that make sense that we should get the answer to diverge? The graph easily kind of, would mean that, say that, right? There's not a questioning here to maybe what it would be. Prove to me this diverges. So how could I use this idea? I'm going to have a limit. I'm going to have an integral. My integral is going from 3 to, it says infinity, but I can't actually physically go to infinity, so that's why we're going to replace the infinity with b. Whatever you want to call it. I used b before, but b. That means my limit, though, when I write it, though, is going to be the limit as b approaches what, though? Infinity. So I'm kind of replacing that b with this limit. So I'm saying that is what's the integral, really simple, of x squared? And I'm evaluating log at
3 and B.
b and 3. And at the end of all this, when I get done evaluating it, I'm going to take the limits as b goes to infinity.
So you start with the top and the bottom.
So whenever I plug in my bounds, I start with the top. So I'm going to first plug in the top one. So this would be 1/3 what? Plug in what? 1/3. Don't even plug infinity yet. We'll take the limit at the very end. So 1/3 b to the third. And then minus 1/3 3 to the third, right? Which is 27. I'll do this side. This is 9, minus 9. What's this limit going to be? Well, I plug infinity in for b. Infinity's cubed is? My kids know that now, which is crazy to think, right? So I get, this is infinity. What's infinity minus 9?
Infinity plus
Infinity.
So if I get infinity, what's my answer though? It's gonna converge, diverge. So we say that our integral diverges, we have this infinite amount of area there. And again, the graph though, you can almost allude, sometimes you can graph, you can actually just look at a graph and probably make a pretty logical guess what should happen. Thumbs up, thumbs down? Not terrible? Can I show you I'm going to show you one other case, and then I'm going to leave you with one, maybe the ultimate calculus problem up to this point in time, right? So that,
Now, what about that extra credit problem? With the hallway and stuff, that was
hard. Yeah. No one wanted to try it. What's that?
I looked it up.
We can talk about it. Yeah, we can.
Nothing's impossible.
Thank you, Josh. Including this one. This is a special case. Do I have any? This is looking like an improper integral.
No.
No, this is a definite integral, right? Except for, you know, what's this 1 over x squared? I keep using this one just because it's a great one to pick on a little bit here. What's this graph look like? What are they asking? What's this mean from -2 to 5? -2 is right here. 5 is right there. I want to know the area under this curve. What's the issue with finding the area under this curve? This is going to go on forever there. This is going to go on forever there. Because my function it's discontinuous. Where's it discontinuous at?
0.
Did I spell that right? I'm going to have to break this up into kind of 2 pieces here. And this goes back to this idea of this type 2 here. If my function is discontinuous at some point, we call it c right here. In our case, what is our c? It's at 0. I'm going to have to divide it into kind of the left of that, to the right of that, and I'm going to actually have 2 different integrals because my function is going to be going to infinity at 0. So my question to ask of you is, how would I write this in 2 different integrals? So -2 to, I'm going to give it some value. I'm going to call it, I don't know, what do you want to call it? What I call it back here, just to keep it consistent. I called it, actually we're doing this one, I called it k, but you can call it whatever you want to call it. But now what is this k though? This is my limit as k approaches what though? Where's it discontinuous at?
0.
At 0. So I'm going to take this limit as k approaches 0. So what happens? I go from -2 to 0 of this integral. But I also need to add, that's the area of one side of it. What's the other one? But again, I'm looking at it this way. I'm approaching it. I got to approach this discontinuous place from the right here, right this way. So as k approaches still 0, that same c value. It's just that where am I starting at though? I'm starting at k. I'm starting at this place where it's discontinuous, and I'm going to what though? Going to 5. So my order is still the same. You know, it's from leftmost point is on the bottom, the rightmost point on top. Again, 1 over x squared dx. Now here's what I'm going to warn you about. Can I warn you about this? When I have these 2 pieces on this type, you could work out, you know, both of them at the same time, just work your way down. But what if I work, you know, this side out and I find this to be infinity? And as I work this side down, I find this to be some number. What's my answer going to be? Do I really need to work this side out? Does that make sense? So if you have this type 2, or I have 2 pieces here, I would argue just do one at a time, because if I find this to become infinity, there's no need to even try and do the other side. Let's do just one more practice with integrating and taking limits. Logan?
What if you get an infinity on one side and a negative infinity on the other?
I still diverge. It's still, I'd have an infinite amount of area, yeah. We would say it diverges. What would you say for an answer? I don't know if you could actually have it with it. I think it'd be a no solution undefined because I don't know what infinity plus negative infinity really
Wait,
is.
so how do you know if one's actually improper if it's one like this where it's just 2 numbers?
Say it again. Well, I have to look at the graph, so I don't have to want to graph it. And I realize that at some point in time between -2 and 5, my function's going to infinity. I have this vertical asymptote. So I don't know, which one do you want to do? Which side? Left or right? So if we did the left, so if we picked on this side, we already did this, kind of, right? We already did this piece, so just do the integral. What's the integral? 1 over x again.
And then 1 over x.
And then I'm evaluating this at k and -2. And then at the end of all this, I'm going to take the limit as k goes to 0. Plug in a k, so I have 1 over k minus minus, a negative 1 over negative 2, so really all this comes out to be is it's still minus a half though, true?
Why'd you do 1 over 2?
1 over negative 2? So I'm going to plug negative 2 into x. So what happens now? I take the limit as k goes to 0.
You get a 0 on the bottom.
I get 0 on the bottom, which is undefined, but I'm getting really close to 0. So if I plug something really, really small in here, what's a number over something really, really small? Really, really big. And it's, in this case, it's a negative. That seems weird to say. On the other side, I have minus a half. What kind of answer do I get? I think I wrote these backwards, didn't I? Did I write this backwards?
Yeah.
I think I might have, like using our formula and switching this order around here. But the idea is still going to be the same, though. I get something that's infinite. Is this going to converge or diverge? It's going to diverge all the way through. It doesn't matter what this other side is. No, and you can do the other side if you want to, but it's not gonna. And so we say again, it diverges. So that's the other case here. Let me go back. Let me just double check this. I think using this formula, how did I write this backwards for?
You had the k on bottom the first time here, but on the example, you had the k on top first time.
Yeah. So here's where this is actually to write this way. We should have put the k on top. We should have got a positive infinity out of this, and not a negative. As I'm approaching it from the left here, k is going to be on top minus that a value there. So again, this is my k here. So that's one thing to switch here. I apologize. I wrote out like this.
So it should be
Negative 2 on top and k on the bottom. Plug in there. I ask you one last one. Here it is for all the marbles, everything you're worth. The last one. I know this is a lot, but I want to get to the hardest of the hardest one. So when you walk out of here, you're Roy. I can do this. I can do anything. This is actually a good review question from last week here, or even from Monday this week. What do you think? What's the issue here? What's anybody?
I have a product of two functions.
I have a product of two functions. Oh no. How do you take the integral of a product of two functions?
rapid integration.
What's that?
Rapid integration.
You can do some rapid repeated integration by. Remember this? Can you do this? Right, so this piece right here, this part of it, again, how would I set up my integral though, number one? My integral is going to be from 0 to, call it b if you want to. But what's my limit though? As b goes to infinity, so a lot like before. But then this though is this x squared e to the negative x dx. How do I do this? I would argue probably the rapid repeated would be the faster way to do it. And how do you know to do that? Why did you say that, Josh Balin?
Because you can't use sub or do anything else.
I can't use sub, and we have a product of. So your derive pile, your integrate pile, what would you choose?
X squared.
Good. Do you remember all this, right? This has been a while ago. We've had all this NISA testing break from some of this. So what do you do with the derive pile?
Drive till it gets to 0.
Drive till we get to 0, so this would be 2x, 2, 0. What about my integrate pile, my b prime? What's the integral of e to the negative x? Thank you. Integral again. Integral again. So that's kind of a little side piece here. So if I asked you, what is this integral from here to here? I still have this limit. So limit as b goes to infinity. But what is this going to be based on integration by parts? Plus, minus. So how do I write that out? So negative x squared e to the negative x.
Why is that a negative x squared?
Because this is a negative e right here, so this guy just took the negative from the e, put it over there. And the last one would be plus or minus. Now instead of plus c though, what's different about this though? This is, I have bounds now. What are my bounds? So this now I'm evaluating from 0 to infinity, or 0 to b. So what would you do next though? And this, again, this is a little more complicated, right? This is about as hard as it gets. This is, I like how this is a good question. So what would you do next? You would plug in
B and 0.
plug in b, plug in 0, right? So if I plug those in, this is still limits. We'll do that at the very end. We'll take this limit. If I plug it into b, I'm going to have negative b squared times e to the negative b minus 2b e to the negative b
B's like 2%.
minus 2 times e to the negative b, right? All of that now, what do I have to do with the 0 piece? Minus.
0.
So it'll be minus, and then this quantity, I'll put this in parentheses. Oops, this is a little higher so you can see. What happens if I plug in 0?
0.
I get 0 times e to the 0, which is,
0.
we get a 0 there. This one I'd get a
0.
0, so minus 0 again.
That one you get a 2.
This one I don't get 0 this time, right? What happens if I plug in 0 here? E to the 0 is
1.
1, so actually I get a negative 2. I'll do the hard part for you. 0 minus negative 2 is, you guess somebody did the other one? What happens when I take the limit as b goes to infinity of the other piece?
How do you even?
Yeah, I don't even know.
How do you get negative infinity?
What's what?
Yeah.
It's gonna be infinite. Just plug in infinite.
I would argue it's not going to be infinity.
It is.
It's weird, look at the graph.
If you look at the graph, let's go back. You want to see the graph? I think I put the graph on here, somewhere. I'll bring it down here. So you want to see the graph? What'd you say, Logan?
I said it's weird AF.
This is what the graph looks like. Do you think this would have a finite or infinite area? Maybe a finite. I'd argue there's a finite amount of area here. But how do we do this though? This is my other big question. You guys have all been sitting through here for almost three semesters, right, or 3 quarters here, right? Our lives have been
4, because I was in pre-calculus.
Yeah, no kidding.
4. Gosh,
First period.
how would I take it?
First period.
You've been stuck here. Well, I'm sorry. How would I do this? I want to move this out of the way here. Sorry. How would I do this piece? How would I take this limit?
B or plug in
If I did just this piece right here, let's just do this piece right here. What would that look like?
the infinity.
This would look like almost like negative infinity times e to the negative infinity. What's e to the negative infinity? We're plugging e to a very big negative number.
Infinity. Or
0.
What is it?
0.
It gets really, really small. So this is like infinity to the negative infinity to the 0 power.
So.
That's a what kind of answer?
I hope he tall.
That's an indeterminate form, right?
Oh no.
What are you even saying?
wait, why did you put it
Because
When you
e
do
to another
multiplying
negative
with-
number. Another way to see this would be if you don't like it that way. Another way to see this is like having negative b here to the what is the squared? Right? Over e to the positive b, right? I can put it on the bottom like this. What happens when I take the limit of this though?
well.
This is gonna give me, just for this piece right here, it's gonna give me, I'm gonna have infinity squared. On the bottom, I'm gonna have e to the infinity, which is, I'm gonna get, this is an indeterminate form, but this is in a form that what though right now? Is it L'Hopital worthy? Good. No, don't cry yet.
It's getting worse. It's worse.
Oh, we're almost done.
I only have a little corner.
What's L'Hopital say? What's L'Hopital say? How do I find the limit of just, again, this is just this piece right now.
Drive the top of the bottom.
I have to drive the top of the bottom, so I still take the limit as b goes to infinity, but what's the derivative of the top?
Infinity.
Thank you, negative 2b. The bottom is going to be easy, EB. Now take the limit again. Do I get something that's not infinity over infinity, or negative infinity over infinity? I still get a negative infinity over infinity. Gosh. So we have to do what?
To run.
Yes, so do it again. We're getting close. Sorry,
All you
paper.
have to do is for every single
No, not
Only like 5.
only half of them. But no, I'm kidding. It might be a
So, like,
question.
you don't know.
What about next? Now negative 2.
Negative 2.
Ooh, this is gonna be good. E to the b again. This, am I gonna get something that's indeterminate?
Negative 2.
No, what am I gonna get?
Negative 0.
I get negative 2 over infinity, which is, that's not indeterminate, that's an answer. What's a number divided by something huge?
0.
Something really, really small. This actually is 0. Woo! So if I ask you this, what's this one right here? That's what we just did, right? We started with this, we wrote it like that.
So that's 0.
This is 0. Yay. Now this, again, this next one is really this, negative 2b over e to the b is another way to write that, right? Just like we wrote this as negative b squared over e to the negative, or e to the b. This one would be negative 2 over e to the b. But wait, have we done this one?
Yes.
Hey, we did. That's this right here, right? What's that turn into?
0.
Hey, done. So this is, minus 0, I guess, or plus 0. And this one would be
0.
So here's my question asked, not losing sight of this little plus 2 here, that I did for you. Note to self, right? That was hard. What's my answer, though? I get 0 on this side.
You get 2.
So what's my answer? My answer is 2. This says, and again, we're looking back at the graph we can barely see here. It could be a finite amount of area there. And so this would say that my integral here actually diverges, converges, the word.
So is it
Now, talk to me.
There's only diverge if it's infinity or negative infinity.
So if my answer is infinite, whether positive or negative, it would be a diverge case. Now, isn't it all, Caitlin, you said, are they all gonna be like this? Not at all. But this is really this is like the top of. Look at the things you just did right here, right? You did. What did you do? Number one, you found an integral, right? Not just any integral. You found the product of functions, which was a integration by parts worthy. We then, after we did all that, we were able to take a limit, right? A limit, so we did some definite integration there. But then, even with my limits, we had to use our wonderful L'Hopital because it was indeterminate. This is like everything you learn in calculus and one. The only thing we didn't do here is we didn't do like the u sub that we do some derivative in here. That's the only thing that's kind of disappointing, I guess, but of what it is. Now, this is actually about perfect, right? I'm going to ask this to do a little bit. And Caitlin, you said you're going to be gone, but I'm going to ask you to do a